Yeah, thanks a lot. So it's great to be here. It's also great to see so many faces live. You know, in the last 3 years, we had some SPICE workshops where I saw 80 tiles of Zoom. So this is a lot better, seeing 80 people alive. In 3D, as someone wrote, not just 2D. Today I'm going to show some experimental results, and I'm kind of going to change gears a little bit from a lot of really exciting theory talks which you have seen to some of the banal problems that experimentalists actually face. So I'm local from Mainz, and I'm also have a co-affiliation at NTNU. So firstly, also for the students, why are we doing all this complex stuff? I mean, obviously it's exciting science. But if you look at what is already in the market, you can see that actually there are already spin transfer torque devices which you can buy, and they work by polarizing current in a polarizing layer, and the current, these electrons which are spin polarized, then go to a free layer and change the magnetization of the free layer. And this is really good. It works, you can buy it, it's actually a product out there, but it is also limited by an efficiency of 1 h-bar per electron for spin transfer torque. And that is, of course, something that fundamentally means that you need a certain amount of current, a certain amount of spins in order to reverse the magnetization. And we heard from Laurent this morning, if you go to low magnetization materials, this can actually improve things. But fundamentally, we are still limited. For every electron that has a spin of h-bar over 2, it can flip from plus h-bar over 2 to minus h-bar over 2, so transfer only 1 h-bar. And the same also holds when you look at things like domain wall motion or skyrmion motion, that when the electron goes across a domain wall, then in the adiabatic limit, it just switches its spin from up to down. So by 1 h-bar, so you transfer 1 h-bar onto the magnetization of the domain wall, and that then limits the domain wall velocity. Now, of course, we all know, because we're here, that there is something more than spin angular momentum, and that is orbital angular momentum. And so with this, it was shown that you can transfer more than 1 h-bar per electron if you have multiple interactions of an electron, say with the domain wall, as the electron passes across it. So this is fundamentally a really exciting opportunity that you can increase, and it's been shown experimentally, a factor 10 in terms of the efficiency of the torques compared to the previously used spin transfer torques. So the spin orbit torques, which is kind of the next step beyond spin transfer torques. This is something which you already heard also again from a few speakers before. There are two fundamental mechanisms, which is the spin Hall effect. There's a nice review from Hyro. And this is essentially spin right electrons which are scattered or with intrinsically moving to the top interface, and then they diffuse into a ferromagnet, and then they act on the magnetization. And now comes again the experimental banality, and that is what we can measure is only the direction of the exerted torques, or even worse, we only measure effective fields which either have the symmetry of a so-called damping-like or field-like torque. And that's all we can provide you with. So please, theoreticians, believe us, we do not measure a spin Hall effect torque or Rashba Edelstein torque. What we measure is an effective field. And we can tell you the symmetry of the field, and that's it. And all the rest is indirect interpretation. Now, in addition to this bulk effect, which is the spin Hall effect, you also have this inverse spin galvanic effect or Rashba Edelstein effect, where we have a non-equilibrium spin density that forms for current flowing at the interface, which then also exerts a torque by exchange interaction on the magnetization. So this type of torque that is exerted can also have the two symmetries of damping-like or Slonjewski-like. And now there is a lot of literature, and now for the students, some people call this damping-like torque, Slonjewski torque, or anti-damping, or in-plane, or anti-dumping, which I thought was really nice. I need to find out the paper. It's a published paper where it's an anti-dumping torque. Okay. And there's a field-like, which some people also call the effective field, a Rashba-like, perpendicular, out of plane, and so on. Now, what we are always interested in is, of course, if we are fundamental physicists, to understand which torque originates from which origin. And again, we also have these orbital effects that I'm going to talk about next. But again, please remember that the only thing we can provide you with is the strength of the effective field, which is millitesla per current density, so millitesla per amps per square meter, and the direction, so the symmetry, if it's a damping-like or a field-like torque. And now we need the input from the theoreticians to actually see what do we have to vary in our samples in order then to understand where one talk originates from. And that is actually quite tough. When I started the business with spin orbit torques in my group, I don't remember, 8 years ago or something like that, everyone was saying spin Hall effect generates a damping-like torque, Rashba-Edelstein effect generates a field-like torque. And that is absolutely not correct. So I think we have meanwhile established that both mechanisms can generate both torques, also theoretically, but also that a lot of simple experiments, like varying a thickness of a layer, are not sufficient, because when you vary a layer, you change interfaces, you change strain. There are a lot of things that can happen. So it is a difficult task, but it's not to put you off. So for the students, this is super exciting because we suddenly have big effects. I wasted my youth on permalloy. Permalloy has nice domain walls, and you can move them with spin transfer torque, but it's a very small effect. The fields are a few Ørsted per 10 to the 12 amps per square meter. In spin orbit torques, we already have 10 times more. We have millitesla per 10 to the 12 amps per square meter. And now with orbital torques, I'm going to show you another factor 10. So we are 100 times better than where we were at 20 years ago when I did my PhD. Okay, so that's kind of the introduction. Now comes the interesting and difficult science. You already heard all of this. So in an analogy to the spin Hall effect that generates a transverse spin current from a longitudinal charge current, we also have an orbital Hall effect that generates a transverse orbital current from a longitudinal charge current. And we have an analogy to the inverse spin galvanic effect, or the spin Rashba-Edelstein effect, that generates a non-equilibrium spin density at the interface. We can generate by the orbital Rashba-Edelstein effect a non-equilibrium orbital density at the interface. So, okay, now again, remember, we measure 2 torques, and now we already have 4 origins. So actually, there is a lot of scope for getting things wrong. But of course, before we actually go into the details to see what we can learn, let me just, my summary of what we heard from Hyun Woo yesterday. So in the 3D metals, typically, we have in a ground state orbital quenching, but when we actually have an electric field or also some other excitation, we can get orbital angular momentum flow or accumulation. And that makes it really exciting. So even though in most typical 3D metals, and apparently what I tell my students in my magnetism lecture course is not wrong, in the ground state, the orbital moment is largely quenched. When you excite it, you can generate a strong orbital angular momentum flow. So I should also say that I'm absolutely new to this field, so there's already tens of years of experience in this. There's some original work here, of course, Dong Wook's work from a couple of years ago. So we came to this experimentally via a lot of motivation from Dong Wook and Yuramo Kruzov to actually understand some of our results. So that's also really nice to be motivated by theoreticians to look for a new effect. Now, one very motivating slide, which I took from Dong Wook, is this one here, where we compare the conductivity, the spin Hall conductivity, and the orbital Hall conductivity. And then we saw that if you compare theoretical calculation of platinum and manganese, we can get like an order of magnitude more orbital Hall conductivity. That obviously is extremely motivating, because I can tell you, after a lot of frustration in permalloy of very small effects, measuring large effects is simply better fun also for the students. So yeah, that motivated us. And there's this work here where they calculated the orbital conductivity and found that for some materials, which for us were not very exciting, people thought very, very large or potentially large orbital Hall conductivities. Now, in addition to the bulk orbital Hall effect, we have also the orbital Rashba-Edelstein effect, where you have a chiral orbital angular momentum texture in K-space that induces the orbital angular momentum. There's an accumulation of orbital angular momentum, which is analogous to the spin Rashba-Edelstein effect. And what is exciting is that it can exist in light metals and oxidic structures like copper oxide without the need for strong spin-orbit coupling. And one has to also point out, again, also for the students, that if you talk to companies like Intel, they're not super excited about using tons of iridium, ruthenium, or platinum, because it's rare, it's heavy, it's also is sometimes toxic to the environment. So cadmium is also a really nice material for some experiments, but I can tell you, if you talk to the European Commission, they're not very happy to have cadmium in any of the devices that you develop. I think if you write a grant proposal, we're going to do mercury and cadmium, might have some issues. But so that is another motivation that I think we should not underestimate, that there is not necessarily now a need for heavy environmentally detrimental and rare and also expensive atom species. So I'll show you later also some results that we have on niobium, which is a relatively abundant and relatively light material. Again, there's some original work here more than 10 years ago, and if you're interested, have a look at that. Now, this is all great. I mean, this, you probably all heard about it, just with a little spin. So now comes the experimental problem. How can we identify? What can we measure? And there are three things. And we already heard about a really nice measurement, which is the Kerr effect measurement, where you just have the single material, I think in this case titanium. I think this is a really nice approach. Of course, as we saw, it's also tough. I mean, nanorad, maybe theoreticians don't realize, but measuring nanorad rotation is not a lot. So it's not so easy. So it's really a nice feat. But we are actually interested in measuring the orbital effects by measuring torques and measuring magnetoresistance. And I think these are the two things that I'd like to walk you through and also show you some unpublished hot results that we just got in the last couple of months. So let's start with the torques. So the first thing that I would like to show is that there are, of course, ways to quantify torques that we use for spin orbit torques. And then there are ways to indirectly infer where they come from. So if you look at these two pictures here, then in this case here we have a light metal, let's assume it's niobium or whatever, where we generate by a longitudinal charge current a transverse orbital current, and this orbital current then enters a ferromagnet. And now, what should it do? There are two ways that you can actually act. It can directly interact with the orbit of the ferromagnet, or as we heard also yesterday, we can convert the orbital current to a spin current, and the spin current then acts on the magnetization. So in the end, what we're measuring is a change, is an effective field acting on the magnetization. You can also have the opposite, which is orbital pumping. So this, I think, was first shown in this paper here. Again, I think we should give a lot of credit to the people that actually did this. A little bit underestimated. I think for 4 or 5 years, no one gave a shit about that paper. Very few people cared about that paper until people actually understood how groundbreaking this was. And then, as you can see, we were like 4 years later. So the experiment that we wanted to do is this one here. We want to measure the torques acting on a magnet. And the first experiment we did was to work on a magnetic insulator. Now, if you have a magnetic metal, you have a lot of things happening. You have current flowing in the metal, you get self-torques, anomalous torques. So I really like magnetic insulators. Not because they're easy to make, they're actually not easy to make, but because you don't have the problem that you have any charge current flowing in them. So anything that happens has to happen by the charge current at the interface. There's no electrons entering into the magnetic material. So what we chose is thulium iron garnet platinum. Of course, it also has skyrmions, so it's an amazing material, and skyrmions are very hot, and everyone loves skyrmions, but I'm not going to talk about it. But just partly we had this material at hand because we were studying in this paper here actually skyrmions in this thulium iron garnet. Then we put platinum on top to study spin orbit torques. And yes, so this is a measurement of the spin orbit torques, and there are different ways to measure that. If you're interested, here's the paper. But what is important is if we vary the thickness of the platinum, we see that it increases and levels off. And that's very typical for all spin orbit torque measurements. So you have initially an increase up to the thickness of the spin diffusion length in the platinum, and then it levels off because essentially all the spin current that is generated in the platinum then further away from the interface doesn't get to the interface, and you maximize the efficiency of the torque here. So this is actually pretty much what we get in YIG platinum, thulium iron garnet platinum, lots of garnets platinum, with something like a spin diffusion length of 1.8 nanometers in the platinum. That's all standard. Now, my very smart student, Shilei Ding, he put copper oxide on top, partly motivated by this existing material. And I was very skeptical because firstly, copper is, light. Secondly, copper oxide is insulating, so somehow, I don't see why it should do anything useful. And thirdly, because he just let it rot at air, which I thought was not a very well-defined process. But then this is what happened. He saw that if you put copper oxide on top, you get a 16-fold increase of the acting torques. So sometimes for the students, do something crazy. And even if your supervisor, or don't tell your supervisor, only tell him when you get the curve. I think that this, he came back with that curve like that, something is wrong. So we did a lot of tests. We checked, what is the conductivity of the copper oxide. We removed the platinum, see what happened. But actually, it's robust. And we saw that for a certain thickness of the platinum, you actually have a strong increase in the torques. And not a strong, but a 16-fold increase. That's gigantic. I mean, we were always fighting for a factor 2. Here, just you get for free a factor 16. So what is happening? The interpretation was that in the copper oxide, you generate an orbital current at the interface. And now this orbital current in the platinum is actually converted into a spin current. And the spin current then generates a spin orbit torque that acts on the thulium ion garnet. And what is interesting is, of course, if you look at here, there's non-monotonic dependence, and that can be described quite nicely because, of course, when you have very thick platinum, then eventually the orbital current that is converted in the first 1-something nanometers of the platinum then simply doesn't get any more as a spin current to the thulium ion garnet. So if you make a lot of platinum, of course, nothing will happen. If you put 1 meter of platinum and you put some copper oxide on top, nothing will exit at the bottom interface. But for thin platinum layers, you have an extremely efficient torque generation, and that means you must have a huge orbital current because you now have 2 times things that need to happen. You generate the orbital current, it needs to be converted to a spin current, and the spin current then acts on the magnetization. So fundamentally, one would say it should be less efficient. Just means there's a huge orbital current that is being generated. Yeah, and then we could fit this and get the length scales of the orbital to spin current conversion in about 1 nanometer. Now, what is also nice about these ion garnets is they have typically nice spin Hall magnetoresistance effects, and then we measured the spin Hall magnetoresistance in the system, and we also found this peak at something like 1-something nanometers of platinum thickness. So here again, this is the series A is a series without the copper oxide, and then we see there is a typical increase and then decrease just because you get shunting. And if you put the in the series B, the copper oxide on top, you have this huge increase, this 16-fold increase, and then the reduction as you get more shunting. And also, we put some, actually, all the credit to Chile, he did it, put also MgO to protect the copper from oxidation, so not let it rot in air, and then you see there is no increase at all. So it's really the copper oxide that makes a difference, not the copper in this case. And we should say that a lot of the explanation was supported by Dongbuk and Yoran. Okay, so this is the first thing we can do. So we can generate huge torques by putting some really crazy stuff on top of platinum. The second thing we did is we wanted to look at magnetoresistance effects to see if we can actually also obtain magnetoresistance effects in these type of systems. And here we removed the platinum. So what we did is we just did permalloy copper. This is from my youth. I like permalloy. And so I said, how about we just put permalloy and then copper oxide and see if we actually need this conversion layer. And then for those of you that are into magnetoresistance effects, there are 3 scans that we can do. We can rotate the field in plane, we can rotate the field out of plane perpendicular to the current or out of plane in the current direction. And then if we do this beta scan, then we get the SMR type, spin Hall magnetoresistance type of resistance. In this case, it's orbital Rashba Edelstein magnetoresistance. And we do this now for different thicknesses, but this time we vary the copper thickness. So the permalloy is fixed, but we vary the copper thickness. And what we see is that actually we get an increase with increasing copper. And again, we have nothing on top, so we get copper oxide. And then as we increase the copper thickness, eventually the copper oxide doesn't oxidize through, and we get shunting, and the effect goes down again. Now, what is interesting about this is if we now compare the different thickness of permalloy and the different thickness of the copper, we can see that if we just put permalloy platinum, we again get an increase of the spin Hall magnetoresistance for the first 2 nanometers or so, and then a decrease. But if we put copper oxide on top, we get a different length scale. We get a peak at something like 7 nanometers compared to 3 nanometers here, and a length scale of 5 nanometers compared to 1.83 nanometers here. And that shows the actually magnetoresistance effect must have a different mechanism, must have a different physical origin. So here it's standard inverse spin Hall effect, so spin Hall magnetoresistance, and here we have orbital Hall inverse, or orbital Rashba Edelstein, and inverse orbital Rashba Edelstein effect. So this, I think, is really exciting because now we have 2 means to determine the possible orbital effects that can occur. One is measuring torques, one is measuring magnetoresistance effects. Now, copper oxide is great. Effects are big, but it's also badly defined. You know, theoreticians don't like it. You know, if you talk to Dong-Wook, he doesn't like calculating copper oxide because we cannot tell him what we really have. You know, we don't have good copper oxide. What we have is copper that rots in air. We also do it in plasma, but then anyway. So, you know, then we have Peter. Peter comes up with all these amazing calculations. So this is from this archive paper here. And then, you know, he compares, and it's not only him, obviously there's this work here, there's Dong-Wook's work, and many others. And then he calculates the spin Hall conductivity and the orbital Hall conductivity. And then you just go through this, and you just pick something where you see a peak, like ruthenium. And you select, let's do that. Ruthenium is great. We have ruthenium in the chamber, and therefore we can just deposit it. And you know, we don't need this oxide, which is badly defined. It's also a little bit frustrating if a paper like this comes out, because this is like, you know, 10 years of work for an experimentalist to go through this, and maybe 3 months of calculation. Anyway, so what we did is we picked ruthenium and niobium because they have large orbital Hall conductivity, but they have very small spin Hall conductivity. So that's what we did, and also Dong-Wook did the calculation in a bit more detail for niobium and ruthenium, and we see huge orbital Hall conductivity, and in red, very little spin Hall conductivity. And then we did measurements, and now all the credit to Arnab Bose. He's a postdoc working with me, and the paper that we just finished is from him, and he will show details tomorrow in the poster. So what we measured was niobium, iron cobalt boron, and niobium nickel, and we measured the acting torques. And we first measured with iron cobalt boron, which is our standard system for TMR junctions, and the torque is super small. We see virtually no torque. And then we measure on nickel, and we have a huge increase in the torque. And now this is something important again for the students. This does not happen for spin orbit torques. For spin orbit torques, the effect is big on all ferromagnets or small on all ferromagnets. Here, there's a huge difference in that we have a major difference whether we act on a different ferromagnet, on nickel or iron cobalt boron. So the same holds for ruthenium. Again, ruthenium and iron cobalt boron, very little effect, and ruthenium nickel, huge effect. And the interpretation is that you need to convert the orbital current into a spin current. And that works well in nickel, but it does not work well in iron cobalt boron. So I think here's a huge field also for students to invest yourself experimentally, trying out different ferromagnets to see what ferromagnet makes the best conversion from an orbital current to a spin current. By the way, this was measured by STFMR, just in case someone's interested. Ask Arnab about details tomorrow. And now, I think we had yesterday the question from Kyungjin Lee, how about anomalous torques and self-torques? So what we did is we actually then sandwiched the nickel between ruthenium on both sides so that we have equal interfaces, and then the effect goes away. So it goes away for niobium and ruthenium. So there is no large intrinsic effect in the nickel itself. So this is, I think, also a very important check. Now I said, okay, there's no strong torque on iron cobalt boron, but there's a strong torque on nickel. Can we make actually iron cobalt boron to be manipulated? And well, it turns out we can, because what we can do is we can again inject our platinum layer. So now we have a more complex system where we have ruthenium not directly on iron cobalt boron, but with a platinum layer. And we again put a second platinum layer on the other side to cancel out the spin Hall conductivity. And if you just do platinum, iron cobalt boron, platinum, then the effect is virtually zero. But now we put ruthenium on one side, and we're going to get a large torque. So now we are able to generate a large orbital current in ruthenium, convert it to a large spin current in platinum, and spin current works effectively on the iron cobalt boron. And that is important because companies don't like nickel. Nickel is not a very nice material for an MRAM device. They want cobalt iron boron because they want a good MgO tunnel junction afterwards. And so the fact that we can use just 1 nanometer of platinum to get, again, this very large torque, allowing us to act on the iron cobalt boron or cobalt iron boron, is super important, because then this allows us to actually switch iron cobalt boron, which is what we want to do for an MRAM device. Now, all the credit to Arnab and his poster tomorrow, so please do see his poster. And now I see my time's already up. So this is the people that did all the work. I just get to talk and travel around the world, or travel not so far around the world and give talks. So these are the people that were involved, in particular Arnab, Fabian, Andrew Ross, Xiaoying Yen, Shilei Ding, Sven Becker, Kyung-Jin Lee, Klaus Raab, Andrea De Lucia, and the others as well, in particular 3 staff scientists, Martin Jordan, Gerhard Jakob, and our visiting professor Hartmut Zabel. This is what we looked like last year, and so this is what we looked like last year, now this is what we look like this year. Things are going uphill. Also, a lot of credit go to our colleagues from Peking University who worked with us together with Shilei on these first 2 PRLs. And also, a lot of credit go to the theoreticians that motivated us to get into that direction. So Dongwook and Frank from Jülich, and Jura also from Jülich and Mainz. And then colleagues in Sendai, Sydney, and also the group of Hiro, Helen Gomonai, Karin Evershosetti, who's now moved to Duisburg. And people were measurements, as well as some of the funding and some work on the iron garnets with Caroline Ross. And yeah, most of the work was funded by the German Research Foundation, as well as the EU, and also some from companies. And yeah, with that I summarize. So, I mean, this is the banal thing. Analogous to the spin Hall effect and the Rashba-Edelstein effect are the orbital versions, but they are not easy to identify as an experimentalist. It's not straightforward to say what we measure is due to one or the other. However, there are ways to indirectly infer it by looking at multiple samples with different stacks and understanding how orbital currents can be converted into spin currents in heavy metal layer or layers that have large spin orbit coupling. And this was shown in this first PRL here. We find this very, very strongly enhanced orbital torques, which I found extremely surprising and then exciting, because it means we can go beyond what is the state of the art. We measured the orbital Rashba-Edelstein magnetoresistance, where we saw that we can even get away from the platinum and use a stack just comprising a ferromagnet and a light metal layer. So we have orbital to spin conversion in the permalloy itself, so not necessary to have another layer. However, if you do want to have iron cobalt boron switched, you need this additional layer. And there we find that in well-defined niobium and ruthenium, where we know the crystallite size, we know the crystalline structure, we can tell Dongwook what we actually have, so we can calculate something reasonable. We get a strong dependence on the ferromagnet, which is unique to, at least as far as I can see, to this orbital effect. Is not present in spin orbit effects. And yeah, please see Arnab's poster tomorrow, and there's a nice review that Dongwook wrote, and I contribute a little bit to it. And with that, I thank you for your attention, and I'm looking forward to the discussions.